Am I started? Have I started going live? I don't know. You would think I would have, figured this out by now. But no. Where is. Yeah, I figured this out by now. Yes, apparently I am going live. No. Okay. I can't see my YouTube studio, so every time I do this, I can never seem to replicate what I did last time, which seemed to work. So, anyway, without further ado, howdy. I'm Professor Parks, and I advocate for the advancement of astronomy. So I'm going live a bit early, so I had scheduled this for 5 p.m. It is now 4:50 p.m. my time. And the reason for that is because I have no patience for things. So I was ready, so I might as well just get going. I hate waiting around for things. So I thought I'd take these first 10 minutes to actually talk about or address what I've been doing, and primarily why I haven't really been putting out content. So if you are watching this and you want to get to the sun experiment, that exciting news, then skip ahead like 10, 12 minutes. Let me, first before I do that, let me pop this out. Can I pop this out? Yes, I can. All right, let me pop out the chat and say howdy to Judy, Stephanie, Dr. Nimrod, and Roisin. You are always a welcome sight. Thank you for being here and helping me with this, supporting me with this. Roisin, we really need to get you a wrench. I don't know why we haven't gotten you a wrench. Stephanie, this will be interesting, and been a while since I got in on a live with Professor Parks. It'll be 4 p.m. Texas time. I'm glad you could be here. Judy says it's almost 12 or 22:30. She says, she guesses she'll be staying up late, and thank you for that, but I don't want to be the cause of a disrupted sleep schedule. I know how frustrating that can be. But anyway, so I haven't put out content in a while, mainly because work has gotten in the way. The day job has gotten in the way. And falls are typically falls are typically busier than springs for me because of events that I have, like such as Space Day, and I also teach the observational techniques class 402. So there's a lot of late night observing. For example, over this week, I will be observing. I had people observe yesterday, and I will hopefully, if the weather holds out, have people observing tomorrow, Thursday, Friday, and potentially Saturday. So that's taken up a great deal of my time, particularly since I've been trying to restructure 402. In addition to that, I have started to accept that I have certain limitations as a human being. I'm not happy about that. I would much rather, not have limitations, but one of the limitations that I have is just a finite amount of energy. I'm not happy with how much energy I have, but I only have a finite amount of energy, and so I have to very much prioritize what I want to actually be able to focus in on. And unfortunately, the YouTube channel has somewhat taken a further back seat. I have somewhat deprioritized it. One of the reasons why I have done that is because I am now, I did some advocacy on the Hill for the Nancy Roman telescope, and I feel that my efforts are better suited towards those sorts of goals. The big goal that I have now is GMU has this grand initiative, Grand Challenges initiative. And I am a part of a group of faculty who are trying to establish a space institute here at George Mason, very similar to the ones at Florida and UFC and or UCF rather, Central Florida, and also apparently at Georgia Tech. My role will be to help create and manage the outreach of that institute. And the outreach is not just going to be educational outreach, but I hope that is going to be a large portion of it. But it's also going to be industrial or industry outreach, reaching out to industrial partners, and government outreach, effectively campaigning or advocating to the federal government the importance of astronomy and scientific astronomical missions moving forward. The Institute, the research for the Institute, it's still very much of a work in progress, but I do know that one aspect, one arm of it, is going to be satellite driven. We currently here at George Mason have a NASA grant to fund a mission called Landau, which I've talked about in the past. I have members only videos going into a little bit more detail. I do plan on keeping up with those, but nothing of real note has actually been happening. So there's really nothing for me to say on that score. We're having our first gate review, or they're having their first gate review, I think next week. So things have been a bit stressed. With that being said, Landau is a satellite mission that is going to revolutionize astrophotometry. Right now, our photometric standards basically set a limit to our accuracy to about 3%, simply because of the way that for example, our main photometric system is based pretty much in part on the star Vega. The brightness of Vega is defined effectively as 0 magnitude. It allows for a calibration, so everything is basically compared to that. The issue with this is that at the time, Vega was seen to be a stable star. It did not change in brightness seemingly at all. However, as we got to better and better precision instruments, we noticed that Vega is in fact variable on the order of about 0.3 of a mag, which in today's standard is significantly notable. And so we are limited by that. And so what Landau's mission is to put a satellite up in space and shoot laser beams down at the Earth, specifically down at certain telescope facilities. George Mason will be one of them. And we will capture the light using our telescope, and we will effectively determine how bright the satellite is on the ground. And since we know exactly what the wavelengths will be of the light coming out of the satellite, and more specifically, we will know the amount of power that is being generated within that laser to create that laser, we have a much more accurate way of creating that benchmark or that calibration, that 0-point calibration. And this is going to have implications across the entire field of astronomy. Anything where you are looking at the brightness of something or determining a physical property based on something's brightness. For example, the period luminosity relationship, which is used as a distance marker, that is going to heavily be impacted by this. And it will allow, the more sexy topics is that it will allow a far greater understanding of exoplanets, because as the saying goes, you only know the exoplanet as well as you know the star. So if we can get that accuracy or that accuracy down to fractions of a percent, the more we know about the star's characteristics, that translates to lowering the accuracy or the error bars for characteristics of the exoplanet. And then there's also dark energy and so forth and so on. So that is but the Institute wants to go beyond that. The Institute wants to establish essentially a presence in satellite missions of all shapes and sizes. So that is what I'm involved in now, and it's starting to very much ramp up. I was part of a town hall today where they outlined specifically, well, with more specificity, what this challenge is going to bring in terms of monetary support, how that monetary support is going to be used, and what sort of focus proposals need to have in order to qualify for these things. For myself, one of the things that I'm going to be looking into is actually partnering with someone from mechanical engineering and attempting to get a $100,000 grant to build a observatory off campus, or on another campus rather, whose purpose is to track low Earth orbit satellites, LEO satellites. Geostationary satellites are, from my understanding, we track them pretty well, to a pretty good precision. But low Earth orbit satellites, which are far faster moving, we know much less about. And in terms of things like who's playing by the rules of, satellites are supposed to have a certain distance away from each other. Certain players do not really hold to that all that often, and so the more data that we can collect on the orbits of these satellites, the better. It has implications all across industry and industry and government. So, howdy, Blue Marble Science. So, let's see, Nimrod. Well, if they were talking lasers, I know something orange that needs to be phaser lasered. It's not going to be that powerful. I don't know exactly the specifications of the lasers that we're going to be shooting, the space lasers that we're going to be shooting, but they would not be powerful enough for Dr. Clive Wells, for example, to become the emperor of the world, seated on the moon and shooting space lasers down onto the planet. I believe that is one of his goals in life. Rob, why don't you don't move here and start Ireland's space program? We could call it Rob SA. Well, y'all have a space program, and it's called the European Space Agency. So you already have the ESA. And on top of that, you got the ESO, the European Space Organization, which is in charge of, I always get this wrong. I believe ESA is is in charge of research, whereas ESO is the thing that basically launches stuff into space, I think. But oh yeah, Philip. I have no doubts that Philip can boost the laser. He has been in the satellite industry for, from my understanding, a couple decades now. So I've been learning quite a bit about how the legal framework of how satellites work, the challenges facing satellites, satellite technology, and things of that nature. So I'm actually I'm excited about being a part of this for a number of reasons. The least of which is that I'm getting a glimpse into a part of aerospace industry that I never really got to see at all, and that, of course, being satellites. Rob So would be 100% potato powered. Well, all right. Hey, if I can get funding, I will go with that. So anyway, it's 5:00, so we are now, it is now time for the purpose of this actual stream. The title of the stream is How Big is the Sun? Experimental Results. So what I wanted to do is somewhat informally present results of a series of observations that I took basically over the last year or so, and with the sole purpose, or the first goal of which, is to get a measure of the angular size of the sun as a function of calendar year, and to do so with a fairly high cadence. And I'll explain that later. And what I wanted to show was that the angular size of the sun changes smoothly as a function of calendar year. So, we've always, or a lot of people have put up pictures of, oh, this is what it looks like in the summer, this is what it looks like in the fall, winters, spring, and you can see the size change over that course, but you don't get a feel of how it changes from day to day. So I wanted to at least show sort of the functional way, or the way that the sun does smoothly transition from a smaller size to a larger size back again. I was also hoping that my observations would be precise enough that I could actually determine an orbit from them. So not only would I be able to demonstrate that the angular size of the sun changes, but I would also be able to show that the path of the sun, or the change of the sun's angular size, corresponds to an elliptical function with an eccentricity of 0.011, which I believe is the eccentricity of the Earth. So I want to be very open about what this experiment does and the errors involved in this experiment. Because I don't want to go into this making any assumptions as to what is going on. I am simply looking at I'm only reporting the results of angular size of the sun. I will leave it to the viewer to verify mathematically the following sentence: that the angular size of the sun is equal to the linear size of the sun divided by the distance to the sun. So if you know that number, if you know the angular size of the sun, then you know the ratio of its linear size to its distance. So if you were to assume or independently determine one of those two things, then you know the other. Now, Aether Cosmology, let me see if I can pull it up because I don't want to get the numbers wrong. Aether Cosmology has apparently improved, has included within their celestial theodolite experiments some way of determining the height of the sun as a function of time, I guess. I just heard about this, or I think Alan told me about it a few weeks ago, and I just haven't had the time to really look into it. I really start seeing this when Alan was presenting it on Earth Awakenings. And then this morning, or what have you, I looked over on their server, and I discovered this. According to them, the moon, lordy, they did not include units. Shame. That would be -1 for every number that you quote if you were in one of my physics lab classes. Sorry. Also, your sig figs are probably a little problematic, so that's probably another -1. Anyway, I jest. They are giving, I'm going to assume this is in miles. If it's not, somebody from the Celestial Theodolite camp can correct me. But they are claiming that the moon is 6,276,000 miles away. Now, again, no units, so that could very well be feet. I don't know. But I think I remember from yesterday, these numbers are in miles. The sun is then 6,370,774 miles. Stars are then 6,317,000 miles away. It's interesting that the way the ordering goes, the layering goes, is that the moon is closest, stars are then next, and the sun is actually further away from that. Again, I apologize to the celestial theodolite community if I am misrepresenting this somehow. I am simply looking at a post by Goose on your Discord. So where this ties into is, as I said, if you can make an assumption of the distance to the sun, or make an independent measure of the distance to the sun, then you know it's linear size. And that has implications for, all right, if I have a linear size, now I can start asking questions like, what makes it burn? Or why is it bright? What is it actually made out of? So you can start answering these questions. So I wanted to do what I could to present data, actual data, verifiable data, because I have posted the images onto Google Drive, so anyone can access them. And yeah, publishable data that people can investigate of their own, and with error, and so with a confidence associated with it. So let's get into the nitty gritty of it. So the method, or the instrument that I used for this experiment was a Seestar S50. This is one of the smart telescopes, and I'm not going to, as much as I want to try to sell this thing to you, I'm not going to. All I will say is this thing is a marvelous instrument. If you have any sort of interest in doing astrophotography or exploring images of the night sky as they are, then definitely look into the Seestar. At a price point of $500, it is the easiest and least expensive way to get into the field of astrophotography, where you are in fact taking pictures of the night sky, very pretty pictures, and I'll show some of the ones that I've taken. It is a 50 centimeter apochromatic refracting telescope, effectively, meaning that it does not have aberrations due to chromatic refraction. Chromatic aberration, which is because of wavelength dependent refraction. I don't know the specifics of the chip. I will ultimately be writing this all up into paper in the winter, during winter break. And so if you're really interested in all the nitty gritty details, I will be posting that paper on my Discord or on the Google Drive on my website, and hell, I may even actually submit it to archive. But it uses a Kodak chip. Now, let me do this. Oh, that's not what I wanted to do. All right. So let me first start off by showing you an image of what the Seestar, an image of a Seestar. Let me first start off by showing you an image taken using the Seestar. I know this isn't very, let me stop being vain and open that up for you. And so this is the Eagle Nebula, or M16. If you go further in, let me bring this in. If you go into the center of this image, you might see something that is vaguely familiar, particularly if you're a fan of Hubble. You have these, this, and this. These are known in the Hubble image as the pillars of creation. What we're looking at is a gas cloud, a molecular cloud, where stars are actively forming within these columns of dust. This is what we refer to as a stellar nursery. This particular image is a a stacked image of 46 minutes. Again, I'm not really going to get into what that means per se, but I just want to show you that in 46 minutes, I was able to take an image of the Eagle Nebula that looks like this. It has been slightly edited to bring out color, but outside of that, it is as you see it. So that's a 46-minute exposure. This is NGC 261. This is a 61-minute exposure. And this is, again, another star-forming region. Now, oops, I keep hitting the wrong button. So those are the types of image that you can see. You can see that the image that is taken is rectangular. So it has, the width dimension is shorter than the length dimension. If cost wasn't important, you could use a C14. You know, honestly, no, I'm not gonna get too far into it. What I found is it depends on the camera. If you're trying to do multi-filter, or if you're doing 3-color imaging, as in you take a BV&R or rather a blue, a red, and a green image, RGB, that is very difficult, regardless of your your setup, regardless of your scope. Now, if you stick a DSLR on the back of it, or a color CCD, then yeah, definitely C14. I'd definitely go with that. And no, Nimrod, it was not Photoshop, actually. It was Google Photo was where I made that simple edit. Anyway, you can see that the width dimension is shorter than the length dimension. And the field of view of that image. So if we go back to this, the field of view, or the fraction of the sky that we are seeing in this image, is 0.7 degrees by approximately 1.2 degrees. I should have that. I'm confident of the 0.7. I'm fairly confident of the 1.2 degrees. So 0.7 across degrees, and then 1.2 or so degrees going up and down. So this is important. Knowing how big of an area is important to note if I am trying to determine the angular size of the sun. Angular size is how big on the sky the sun appears. So the first step to do this is you need to determine something known as plate scale. You need to know what is the amount of angle that corresponds to each pixel. So if you only had a 1-pixel camera, how much of the sky, what is the field of view within that pixel? So how does one determine that? Well, you do that a couple of different ways, which, where is it? This way. So this is not nearly as an exciting an image as previously. So bear with me. This is a 20-second image of a open cluster, I believe, called IC 405. I know, very romantic. She loves long walks on the beach and pina coladas. Reason why I chose this particular region of the sky is that it's extremely well studied, or it's well studied. It has very bright stars within it. So the positions of these stars are very well known. And really what I did was I took a smattering of stars. I think I took about 10 stars within this field of view, and I computed I measured the linear distance on the chip, like the pixel positions of one star relative to another. And I did that for, like I said, a sampling of about 10 stars. I then know The longitude and latitude coordinates, effectively, in astronomy, we refer to the stellar longitude of the stellar longitude is the right ascension, and the stellar latitude is declination. So I have the longitude and latitude coordinates. I have their positions in the sky. And so I can determine the distance between those two points using the distance formula. Now, I did this one of two ways. One way you can do it is you can use just Pythagorean theorem. A squared or C squared equals A squared plus B squared. It's just simply just a distance between two points on a plane. But that is technically improper. Because we are looking at the celestial sphere, a basically 2D spherical representation of the sky, you really want to use spherical trig in order to determine the distances between them from an angular standpoint. As it turns out, I did it both ways. As it turns out, because the angle is so small, the numbers basically are the same. I still use the spherical trig numbers, but effectively, given the accuracy of my measurements, it doesn't matter. It ultimately didn't matter. So I now have the angular distance. I measured the linear distance across the chip, and now I have angular distance per pixel. So now I have what is called a plate scale. I know what is the angular size of the sky that is viewed by 1 pixel. And I calculated that to be 2.374 plus or minus 0.3911 arc seconds. So every pixel that is on the sky corresponds to roughly 2.4 arc seconds. Now, how does that apply to the sun? If I have an image of the sun and I can measure the number of pixels that go across its surface, I can then multiply it by the pixel scale in order to get its angular size at the back end. You notice that I quoted an error. I know this, 2.37 plus or minus 0.39. That is the confidence level that I know the pixel scale. And I determined that based on the standard deviation of all of so I determined pixel scales per pairing of star. And so that standard deviation, or that error, is a standard deviation of all of those different measurements. That's how I did it. I'm a yank. What is going on? Oh, pina coladas. Hey, I talked to IC 405. We don't kink shame here. So if she likes pina coladas, all right. So what about the star? Or what about the sun? So I went about using the sea star, and I took images of the sun, which was properly filtered, so I didn't burn out the sensor. And I took observations from March 14th, 2024 to May 26th, 2025. I took over 3,800 images of the sun during this time. The strategy was to be able to take an image of the sun anytime that I could. And I would take 5 images each time on each particular day. That way I could determine effectively an error for the angular size measurement for that set of observations. Now, as it turns out, the time between various different observations, I was hoping for a daily record, but that did not happen, and I really wasn't expecting it to happen because of weather, but also life got in the way. But I do have a record where the furthest 2 points, we call that the cadence The furthest time between two observations isn't more than a week, 7 to 10 days, something like that. Generally speaking, I have an observation within a window of 7 days, and sometimes 2 or 3 observations within that time. The exposure times were less than a second. As this process evolved, I figured out more functionality to the Seestar, so I was able to very much tweak the exposure time and the gain in order to get the brightness of the image as crisp and as clear as possible. In hindsight, if I were to do this again, which I do plan, or if I plan on continuing this, what I would do is actually keep those settings static. I would use the same settings for every single observation, because then I could potentially make an estimate of the brightness of the apparent brightness of the sun as a function of calendar year. Right now, all I can really tell from my data, all I can really tell you is the angular size. So this is what one of my images looks like. Oops. Okay. Here is an image of the sun taken on 4/8/2024. And I should mention, of course I would start off with this one. I will mention that all of the images, except for the ones taken on April 4th or April 8th, were taken from Fairfax campus, basically right above my head on our observing deck. I wanted to keep that basically as a control, observing the sun from effectively the same location every single time. Now, you may know that there was some rather exciting astronomical event that happened April 8th, 2024. That, of course, was the solar eclipse, total solar eclipse, and I got the privilege of watching it at the Indianapolis Motor Speedway. And so I was able to determine the longitude and latitude of that position, and I have corrected that, or I have included that within the analysis. So I have included where the location is for all of the observations, and so that has essentially been taken out of the equation. All of the images are as if they were taken from the same place. You can see there are sunspots, a couple sunspots here. I'm going to show you a couple of other ones. This was taken Fairfax on May 13th. You can see there are, I don't know if you can see my cursor, but there are a number of different sunspots groups that you can see. Here's one with more prominent star spot grouping or sunspot groupings, like that one, for example. So you can definitely see the umbral and somewhat of the penumbral structure, but you can really see the active region. I'm sorry, umbral, and this is the penumbra. This shadow, this lighter shaded area is the penumbral part of the spot. So those are the ones that I was able to. Those are a representative of the images that I was able to take using the Seestar. Now, how do I measure the size of the sun in those images? And I wanted to do so in a quantitative way. I first started off attempting to do it by hand, essentially drawing a line across the image in GIMP and looking at effectively where the brightness changed to a certain degree across that across that line, looking at the profile of brightness as a function of pixel position, and basically making some kind of determination as to where the edge was, and then measuring it that way. But what I found is that it was far too subjective for me, and I was like, this has got to, I can code this. This is something that I can write a program to do for me, which greatly reduced the amount of time. It was taking me days to analyze, or many hours to analyze only a few images. Whereas once I've written the code, it takes, I don't know, less than 10 seconds for it to pump out the results. So no, there's definitely no GIMP shaming here. So that's what I did. I measured the angular size across the entire board of all of this data. And this is what I found. So the blue dots are my observation, the angular size observations. The red dots are the expected size of the sun as determined through the ephemeris used by Jason Mias in his book Astronomical Algorithms. I can get the particular date eludes me. I did not use Stellarium for this. I actually used a JPL ephemeris, determined ephemeris for the sun, and determined based on those orbital elements what the expected size of the sun is at that time. So what this is saying is that the expected points, the expected size that is being shown is the heliocentric model. This is the size this is the size due to the consequence of a reasonably constant radius sun that is 149 million kilometers away, and that the Earth is traveling on a very slightly eccentric orbit. And as you can see, the data matches pretty well. The residuals are, the bottom of the graph are the residuals. And so what that means is I've taken the data points, my data points, subtracted off the expected, and that shows you how much deviation there is as a function of time. Now, one of the things that I haven't done yet is actually determine the numerical value of that. At least I don't think I've done that. Where is it? Let me run this. Oh, didn't like that for some reason. Why didn't it? Okay, I don't know why. But anyway, getting lost in this. I don't think I have, but I'll have to double check. Again, I'm going to be writing this up. But at the very least, you can see the deviation off the expected is less than 0.25 arc minutes. It's less than plus or minus 0.25 arc minutes. And I would say that it's actually even smaller if you were to do the root mean squared of this to determine a gauge of just how deviant my observations are to the expectation. I would be surprised if it were, let's say, 0.2. My observations match the expectations to 0.2 arc minutes. Now let's look at what the observations are telling us. Well, first off, you can see that there is a sinusoidal behavior to the sun's size. That the sun size does change as a smooth function over the course of the calendar year. This is theta is the angular size in arc minutes. The x-axis is right ascension in hours. Right ascension being the stellar longitude, which in turn is effectively a measure of calendar year. So we can see that there is pretty much a smooth transition around across that year, going from an angular size of approximately 31.1 arc minutes to all the way up to about 32.5 arc minutes. So almost an entire arc minute change in angular size of the sun from the beginning of the year to the end of the year. You can see that my error bars are considerably less than that. So again, one of the things that I still need to do is I need to compute the statistical significance of this variability. But I hope you can see that we're talking about at least a 3 sigma event. We're talking about something that is clearly the amplitude of this pulsate, or the amplitude of this change, is far larger than the individual error bars for these observations. So yes, the orange line correspond to the solstices. And so the first one corresponds to the summer solstice, and the second one corresponds to the winter solstice. And what you can see is that during the summer solstice in the northern hemisphere, the sun is actually the smallest that it gets. During the winter solstice, it's the largest that it gets. Although what I found to be peculiar, and this is not something that I actually knew and I'm wanting to investigate, is that there is an offset. It's not exactly at the point, the minima of this sinusoid, and this is not the maximum of the sinusoid. There appears to be a phase shift. The minimum and maximum appear to shift by, I don't know, a few days from the actual solstices. I suspect this has to do with this is caused by the ellipticity of the orbit, but that's merely a guess at this point. But anyway, it verifies also something else that the heliocentric model has stated, is that in the summer, the angular size of the sun is smaller than it is in winter. Now, what does this tell us? If we are being honest, what does this actually say? Howdy, Tony. What I'm measuring is the angular size of the sun, which is the ratio of the sun's size to the sun's distance. Linear size to the sun's distance. Now, I have demonstrated, I think fairly conclusively, that the sun's angular size changes over the course of the year. That means one of two things. One, the angular size, or the linear size of the sun, is changing as a function of time, or the distance to the sun is changing as a function of time, or both are changing as a function of time. Now, I've shown you that I guess I'll show it again. The red dots are the expectation. Those are the angular. That is the angular size of the sun, as determined through a JPL ephemeris, as quoted by Jason Mises. He gave me the orbital elements, and so I was able to determine the distance or the angular size that way. And again, this is the heliocentric model, if you will, where the angular size is changing based on the fact that it is moving, the Earth is in an eccentric orbit, and the Earth's distance to the sun is changing as a function of time. The sun's linear size does not appreciably change over the course of a year. It does actually shake a little bit, pulsate a little bit, but not nearly on this timescale. The timescale is much shorter, and the pulsations are much less than I would not be able to detect them with my instrument. So So that is the expectation. So right now, my data is in support, and I would say that it is in significant support of the heliocentric interpretation of what is going on in terms of the angular size of the sun. Now, in terms of flat Earth, or in terms of people who are skeptical of the heliocentric model, what needs to be done, and I want to stress this very much, I want to very much stress this, is that what I have done, again, to put it plainly, is that I have a model. That model makes a prediction. Those are the red dots. That my model predicts that on any particular day, the angular size of the sun will be a particular value, a particular size in arc minutes. I then made a series of observations, and I made measurements of the sun through those. I made a measurement of the sun over the course of the year, and I compared it. My observations are independent of the expectation. All I did was measure the angular size of the sun on a particular day from an image that I took of that using a smart telescope. So, if you are skeptical of the heliocentric model, as it were, if you are going to convince me of this, if you're going to convince me that there is a different explanation, then you need to develop a model mathematically that makes predictions as to the angular size of the sun. So therefore, I can match my data to it. The celestial theodolite folks make a big to-do about hypothesis testing. Well, this is how scientific testing is done. You use a model to determine the expectation of a physical phenomenon, and then you match it to the observations. So what I need to do, one of the things on my to-do list is, one, I need to determine the root mean square deviation of the observations from the expectation. That will give at least some benchmark to test other models. So if someone else comes up with a model that provides expectations, I can match them to my observations. I can do this sort of analysis, and I can determine the root mean squared of the deviations from that model. If the deviation is smaller for that model, I now have evidence in support of a model that is not the heliocentric one. This is how science is done. This is how models are tested. It is done so quantitatively, with error included. So, speaking of that, first, let me back up and explain a little bit about how I measured the size. So, I wrote code. I took the image of the sun from CSAR, and then I gave it a certain criteria or a threshold where basically if the brightness of the image dropped below that threshold, I said that those pixels are now black. Effectively, I cut any sort of gradation. So if you take this image, for example, you can see that hopefully you can see my cursor, but if you move away from the sun, you can see that there is sort of still some brightness going away from the sun. And that's simply because of sky brightness, is that the sky around the sun is also getting brighter, or is getting bright because it's being illuminated, and the brightness is extending beyond the actual angular size of the sun. So what I attempted to do was wrote code to get rid of that. I effectively, again, said anything below a certain threshold is now 0 in terms of pixel size. I then, the code would then determine the actual position of the pixel, where that transition happened. That is the green line. And the red line is effectively a circular average of that. So that is how I determined the size of, that's how I fit the size of the sun, or determine the size of the sun. Now, did this work for every image? No. For reasons that I could not figure out. For certain images that I took, in this case, the image, I went a little nuts with the exposure time and gain. The image is so bright that the code failed. It just could not figure out what to do with itself. So there are maybe 20 some odd images or so that I could not use because the methodology just failed. So, but that is how I determined it. In terms of error, where do these error bars come from? Well, they come from the fact that there is error in the plate scale. As I mentioned before with the methodology, I took 5-ish images, sometimes a little less, sometimes a little more, but on average around 5 images per observing day. I then determined the angular size for each of those 5. The standard deviation of those 5 now created an error in the size of the size of the sun at that for that particular observation. In addition to that, and I want to be fully transparent, I don't have a plot for it, but I want to be truly transparent. There was or is a systematic bias in my size determination. Effectively, what happened was that it was over predicting or the sizes that it was measuring were consistently larger than actual, I guess you could say. And what I mean by that is that it didn't matter what portion of the year this was happening. It was the size was always a couple tenths of a arc minute larger than was expected. Now, what I then did was I then added a shift. Which, let me see. I recognize I'm probably going to get hammered for this, but again, I am being fully transparent in what I've done. Is that error is, do I have? Nope, I don't have a number for that. I would need to run the code and figure out and have it printed. But the error for that was, again, probably a couple tenths of an arc minute. And again, it was consistent. It was pretty much the same amount, an overprediction by the same amount across the entire year. So all I did was that I shifted the data down by that much, and then I added that to the error budget. So yes, effectively it's a bias correction. Tony, did you consider using the ratio of each pixel to the brightest pixel, or does that fail because saturation occurs? I did not. That is not how no. The simple answer to that question is no. But yes, saturation is definitely going to play a role in that. Although, except for like those images that I showed you where my methodology failed, the images were not saturated. I made sure of that. I actually adjusted the gain in the exposure time so that the chip was not saturated in any way. But one of the reasons why I am doing this, one of the reasons why I am putting this out there is because I want this sort of feedback. I want this feedback from globers or flatties or whatever. I would like feedback on how you think the analysis may be flawed and what I could do to potentially make it better. I would prefer constructive criticism, such as saying, hey, have you considered doing this? And then I can potentially do that and see what that gets me. Systematic error, according to Blue Marble Science, systematic errors are just part of the game. Those can be accounted for and should. Random errors are just about impossible to really deal with. Yes, again, random errors, that's why we have these error bars, is because we cannot characterize them. And so that affects, we cannot characterize them, so therefore we do not know it's hard to characterize them, I should say. So there is a certain uncertainty as to the precise value that we measure. But because we all know the dreaded R word, did I take refraction into account? Well, yes, I did. As I continue with this experiment, again, I hope to do so further on, pick it up again. I haven't taken observations in a few months at this point. But when I pick it up again, what I'm going to do is I'm going to perform the next set of observations a few more times so that, oops, that's not what I want. There we go. A few more times so that I have more confidence in the results. Ta-da! So, what I did was on a particular day, and the day itself escapes me at the moment, but what I did was I took images, again, 5 images at a time, at particular times over the course of the day. Specifically, I did this from slightly after noon, actually 12 p.m., slightly after 12 p.m., to effectively sunset. Now, in astronomy, we don't really talk about refraction in terms, or refraction effects in terms of altitude. We refer to it in terms of what is known as an air mass. An air mass is basically how much of an atmosphere are you looking through. If you look straight up, you have an air mass of 1. As you look lower and lower towards the horizon, you are looking through more and more atmosphere, and so therefore your air mass increases. If you want to know what the angle is, the air mass is the secant of the zenith angle. So the zenith angle is the angle away from zenith. So if someone wants to, they can look at, if they want to know basically how far I went or how far down I went, you can, I think this is probably around 3.4 air mass. So take the inverse secant of that, and there you go. And then take the complement of that angle, and there you go. You get the altitude, how far down I went. And again, I did the same thing again. I computed what is the expectation based on the ephemeres that I found. And the red dots are that ephemera, or are that expectation. You can see there's actually a little tiny bit of decline in the angular size of the sun. And we always say that the angular size of the sun is constant over the day. Well, apparently, technically, that is not true. There is or at least there appears to be, according to this, particularly if you look up here, the first 4 observations, there is, the sun does appear to get slightly smaller as it goes across the sky. Now, we're talking arc seconds of it getting smaller. I don't know really how to even care. I mean, I guess I could figure out how much it's actually changing based on the mean observations. I suppose that's something else I can look into. But that's not unexpected. That doesn't actually violate or cause consternation for the heliocentric model, because you are, as the Earth rotates, you are literally getting closer and further away from the sun as the sun gets up or rises and sets. What I would contend is that it is not nearly as significant as the angular size of the sun would change as a function of hour on the only flat Earth model that I can see, or that I have been aware of. I'm going to table that for a second. Really what I want to point out here is the observations that I took. And so again, I took observations. I used the error. Howdy, Maya. Welcome. The error bars correspond to the errors of those observations, or those individual sets of 5 observations. And what we can see is that there is a clear trend that the sun gets smaller as as the sun goes down. This is expected by refraction, or the expectation for why this is occurring is refraction. And again, I want you to note that this deviation is on the order of 0.5 arc minutes. Whereas the amplitude is 1 arc minute. Actually, is it 0.5 arc minutes? Actually, yeah, no, about 0.3 arc minutes, somewhere in there. I'm sorry, 0.03 arc minutes. That's better. That makes me feel better about myself. About 0.03 arc minutes. In comparison to 1 arc minute deviation, this is basically nothing. But I went ahead and fit it anyway. And so I did a linear or a least squares fit to this data. And you can see up in the corner, this is the fit that I got. So what I then did was I took my observations. I figured out what the air mass is for each of those observations. I then put that into this equation, and then I found a correction. I found the correction for, or a corrected, or a refraction corrected size. So after I've applied this correction to the observations, I have now effectively corrected for the size change due to the fact that the sun will shrink based on air mass. So yes, so this is where I took this into account. Each of these variables, the slope and the intercept, also have error bars, but for brevity, I did not include them. But I also then added a term to my error budget that corresponds to the error in this analysis. So I have not just accounted for the error I have not only accounted for the refraction effect, but I have also added to my error budget the error in the fitting of said refraction. And so this is the point that I really, really want to stress, is simply taking observations is insufficient. You really need to figure out where are your sources of error And how do you take into, or confounding variables for one thing, how do you take confounding variables into account? And how does that affect your overall error? Because again, the amount of error is going to indicate how much trust I can give these results. The error for these observations are on the order of 100 or 0.01 arc seconds, thereabouts. Whereas again, the deviation is on the order of an arc. The error is on the order of 0.03 arc minutes for each individual error, for each individual observation. Some observations have better error, some observations have worse error. It depends on the observing conditions of the day. And, but the error bars are very much smaller than the deviation itself. So I have a high confidence that I am actually seeing the behavior of the angular size changing as a function of distance. And so when you are attempting to develop a model or really do science to explain an observation, you need to be able to identify any confounding variables, and you need to be able to determine what are the sources of error in your observations. And you need to be able to give an explanation as to where those errors are coming from. And if you believe your errors are so minuscule as they wouldn't appear on a plot, I would encourage you to rethink that. It is very, very rare that an experiment is designed such that the errors of those individual measurements is so small as to be basically nothing. So that's there. One of the things that I want to do, again, one of the improvements to this project that I want to do is I actually want to see if this relationship fits to known refraction law or known refraction functions. So there are a couple of different laws that indicate differential refraction as a function of error mass. I would be curious to know, I would plot those expectations across this data set, and I would be curious to know what the if these observations actually match those. If they do, then I can be very confident that this effect that I'm seeing as a function of error mass is in fact due to atmospheric refraction and not something else like stellar pulsation or something of that nature. So we have Thurston, how would the Python code react to an oval sun? Refraction would tend to slightly squish the sun as it drops, thanks to the bottom being raised up slightly than the top. Yeah, that's differential refraction. Now, the code assumes a sphere, or the code assumes a spherical. I can speak today. The code assumes a circular sun, so it does not allow. It does not fit an ellipse to the sun. It only fits a circle. The reason why I was confident in, or why I was comfortable doing it that way, is that the difference in the size of the sun from polar to radial or polar to equatorial is far smaller than I would be able to measure. So to me, the sun would actually be slightly, to me, the sun is effectively a perfect circle, at least to the precision that I can measure things. The sun is a perfect circle. You are right, as the sun sets, there is differential refraction, meaning that there's more refraction at the bottom of the sun than there is at the top, and so you get the thing is getting squished, more so at the bottom than at the top as it goes down. I still think that this is an appropriate way of doing things, of still assuming a circular sun, because I, again, think that the amount of differential refraction as a function of polar size to equatorial radius size is still below my precision to measure. So I think that's still within the error or still awash in that error. So yeah. Other things that I want to do is so I have all of these observations. Unfortunately, the cadence isn't. It's pretty gross or coarse, I should say. Like I said, I have observations, at least one observation within a week, maybe two observations or what have you. And what I would like to be able to do is I have these spot patterns. The sun rotates roughly once a month, or about 12 degrees a day. And one of the first ways the observations that Galileo made of sunspots, he rightly determined that the motion of those spots is due to the rotation of the sun. And so you can measure a rotation period for the sun using spots. One of the things that I didn't really get into is that because it's an alt-az mount, because of the way that it's mounted, it's looking at the altitude and azimuth, there's something called field rotation. Basically, if you take an object that is oriented in this way and it is rising, as it goes across the sky, it's the angle of this orientation is going to change as a function. Basically, it's going to appear as if the object is rotating within the field of view of your instrument. This is a well-known phenomenon. It's a well-characterized phenomenon. So basically, what I can do is I know where in the sky the sun was at that time. I know the altitude and azimuth coordinates of that, and I can just make a correction to get everything oriented so that north is up, south is down. Once I have that done, I can then basically look at the images and see if I can identify suns or spot groups that are identical, that are common within one image to the next. Because of this cadence, because of the coarse cadence, I probably would not have a lot of data for any one particular spot group. So I'd probably have data. I would anticipate I wouldn't have more than 3, if I'm lucky, 4 data points of seeing that spot group across a side. However, I have a lot of images, so I have a lot of different spot groups. So even if I only get, a set of data points from one set of observations for one group, I can go through the rest and find other groups and calculate or measure the rotation rate given those motions. Is that kludgy? Fuck yes. Ideally, what I would want to do is I would want to, and I can incorporate this into the refraction measurements, is I can take much finer cadence observations or observations every hour as opposed to every day, or even if I feel like it, every half hour. And then I can use that to see the spot group move. And if I do that on consecutive days, then I should have enough data that I can confidently say what the rotation period is. And what I mean by that is that I can give you a rotation period with a small error bar associated with it. Now, there's also something else that could potentially be gleaned from this data, and that is that our current understanding is that the sun is a differential rotator. So, a solid body rotator is very much like this old gear shift knob, in that as I rotate it, the rotational period of every point on this gear knob is the same. The Earth is a solid body rotator. It rotates once every 24 hours, effectively, or roughly speaking. everyone on the Earth, regardless of their location, experiences a day of roughly 24 hours. The sun is what we call a differential rotator, meaning that the equatorial regions of the sun actually rotate faster than the polar regions. And this is seen by the magnetic fluctuations within the sun. We believe, it is our current understanding that it is this twisting, this differential rotation, or basically twisting of the sun's surface that is the dynamo for magnetic phenomenon. And so if you were able to plot out what the latitude was of the spot, you could determine a rotation period as a function of latitude, and you could potentially see this differential rotation. You would be able, if you were only looking at spots that were in or around 20 degrees, you determine a period of that, say 27 days. Then you looked at spots that were pretty much around 60 degrees. You might get a rotation period that is 29 days. And so you can do it that way. Maya, don't even know how that is possible. Are you talking about differential rotation? Because, that's I wouldn't say it's, I've never heard a good explanation for why the sun is a differential rotator. I would imagine it has to do with conservation of angular momentum, of when it was forming, the the inner portion of it, the equatorial regions were rotating faster than the polar regions because they were basically squashed to a smaller spatial scale or smaller size. But that's a guess. That is a guess. I was thinking refraction squish rather than spin squish. Again, refraction squish I don't think is measurable given the precision of my my technique or my instrument and methodology. If I could figure out a different methodology, then I could, then potentially. The other thing is, right now, the error that I'm associating with the pixel, or basically the size, is just a standard deviation of 5 images, of the size taken for 5 images. What I would really want to do is a Monte Carlo simulation, where I create a just assload of fake images, basically just a 1,000 fake suns of varying different sizes that I know, and then having the algorithm measure the sizes of those, and basically how well it fits then becomes my error for that part of it, is how well does my algorithm actually recover the true size of the sun. But that's a bit more complicated than I have time for, and so I just basically punted and just did the standard deviation way. Does this also apply to Jupiter? Jupiter is weirder. So we often talk about the Coriolis effect, that because of the spin of the Earth, the winds get deflected in one direction or another. Another effect of the rotation is the development of what we call Hadley cells. And Hadley cells are for the Earth. We have 3 in the northern and 3 in the southern. And I'm sure I'm going to get this backwards, because if given a binary option, I will always choose wrong. The winds at the equatorial region of the Earth, let's say, are predominantly westward. The mid-latitudes are predominantly eastward. And at the high latitudes, they're predominantly westward again. They basically are the same rough direction as the equatorial regions, but not as fast. So yes, the atmosphere of the Earth is, in fact, a to a very rough approximation, a differential rotator. For Jupiter, it is far more extreme because Jupiter's rotation because it is so much larger and because it rotates basically twice as fast as the Earth does. The rotation period of a Jovian day is roughly 10 hours or so. Is that you have at least 5 or 6 different Hadley cells in each of the different atmospheres. And the wind speeds are at hundreds of kilometers per hour, and they are in different directions, and they shift in a very short latitude span. So they very quickly go from like hundreds of kilometers in this direction to hundreds of kilometers in that direction. That's why Jupiter looks swirly, technical term. All of those swirling patterns that you see in those gorgeous Juno images, it's because of the shearing of the overall bulk motion of the gas moving in one direction as opposed to gas moving in the opposite direction. That's what causes the hurricanes on Jupiter. It is presumably what is helping cause the Great Red Spot, although I think that is actually a different type of phenomenon. I mean, it's a hurricane. I mean, obviously it's a swirling, massive gas, but the fact that it's so much larger, the fact that it's red, the fact that it's so much long-lived, there's obviously something else going on there other than just simply Coriolis effect. Technically, Hadley cells are only the equatorial cells. The ones closer to the poles have different names. My apologies. I just saw the text that I look for. I learned it as the Hadley cells cover all of them. So I know there's the mid latitudes or the westerlies or whatever. Hey, I got it right. Equatorial winds are towards the west. Yes, in the northern hemisphere, because I am northern biased. I try to recognize that I am northern biased. I like to try to recognize all of my biases, including locational ones. But yes, Judy, that is the reason. That is, yes, Jupiter is definitely a differential rotator. At least its atmosphere is. You also see the same effect in Saturn, kind of, sort of in Uranus if you squint. Not really in Neptune. Uranus and Neptune have rotational periods on the order of, I think, like 13 to 15 hours. And so for whatever reason, and also they are much smaller. So the upper atmosphere is not nearly as, the upper atmosphere is far more diffuse than in Jupiter and Saturn. And so the wind patterns aren't nearly as noticeable. Essentially, you can think of it as Uranus and Neptune are smoggy. They have the larger envelope of hydrocarbons surround the atmosphere and basically blocks out any kind of structures that you could really see from the underlying atmosphere. Jupiter and Saturn also have smog, but not nearly as much. Cue your anus joke, yes. So, all right. That's basically it for my thing. I don't think I have left anything out. I'm looking through my images now. So again, for those who are watching this at home, watching this later, first, thank you. And second, regardless of how you think the universe is constructed, I very much would like to know your opinions on my analysis. Do you think that this is a proper way to answer the question, does the sun change its angular size as a function of calendar year? What do you feel? How do you, and you put them in the comments, please put them in the comments. What what do you, and even if you have suggested some in the chat here, also please put them in the comments, because I will, of course, forget them if they aren't written down. Let me know. What do you think about this analysis? Do you think my do you think my assertions are correct? Do you think the way that I've handled my error is correct or appropriate? Do you know of a different way or a better way that I might be able to measure the size of the sun? Any way that I can actually tamp down those error bars? Because one of the things that I forgot to mention, that one of the things that I wanted to do was to fit, like, it looks like a sine wave. The angle, the change in the angular size looks like a sine wave. However, the heliocentric model tells us that it's not. That it is in fact an ellipse, and so it would be a skewed sine wave. So what I have somewhat attempted to do is fit that that wave to an ellipse with to an ellipse to figure out what the eccentricity is. Well, figure out what the eccentricity is. I'm going to have to, the methodology that I was using was not fitting really the data at all. And the only way that it could make it fit is if I effectively force the eccentricity to be around 0.011, which I was not comfortable with. So I need to figure out a different way of fitting that. So if you know of a way that I can fit that data to an elliptical function where I can get the eccentricity of the orbit of the Earth, I would definitely appreciate that. So let's see here. Thurston, thank you for this. You're welcome. I want to do more of this. This is definitely, when I first started this channel, this was definitely one of the things that I wanted to do, was to do these types of experiments and show the results. I just, again, don't really have the time. I do have observations of a W-UMA binary, which is an amazing object. It's two giant stars that are so close together, they share a common envelope. So if you were in the Starship Enterprise and you were close enough and you were able to properly filter out the light and you were to look at it, this object would look like a peanut. You would not be able to tell that where one object started and the other object ends. It has a rotational period that is much less than a day. So you have two stars that are roughly the size of Venus's orbit, that are moving around a common center of mass, which is effectively the middle because they're basically equal mass, once every, I think it's around 16 hours. Just, to me, it's mind-boggling. Just these immense stars are just moving so rapidly around a point. To me, it's beyond comprehension. And that's not even talking about neutron stars or pulsars and how quickly they rotate. But I love the idea that that could exist, that you have these two stars that are so close together that they share an envelope, that they are in one way a single object. And because they're rotating, they also have spots on them. I have photometry of that, and what I hope to be able to do at some point is to actually finish the analysis on that and see if I can come up with some estimates of the star's mass, the star's radius, things of that nature. I know the period very well, but I don't have it off the top of my head. Dr. Ninrod. Well, if solar winds get stronger and weaker, then would it be logical to say the sun does become bigger or smaller as its fusion fluctuates? It's more complicated than that. So the rate of nuclear fusion certainly does play a part in the amount of solar wind that gets generated. But there are a lot of conflating variables involved, most of them having to do with the magnetic field, because the amount of solar wind is primarily a function of how transparent is the magnetic field. So you may have heard of these things called coronal holes, where there are basically the field lines in the corona are oriented as such that basically that allows the solar wind to stream effectively through and into the solar system. Whereas in other parts, the solar wind gets redirected. It still goes out, but it gets redirected. So, and that's going to affect things. Then you also have the magnetic field is going to inhibit the amount of radiation that is coming out in particular or in particular areas. That's essentially what happens with sunspots. Spots look darker because they are literally colder than the rest of the surface surrounding them, because there is a magnetic field that is causing a diminishing of light. The light can't all go through that area. Some of it has to go to basically gets shunted off to other sides. So if you really look at an image of a sunspot, which of course everyone should, you would see the sunspot, you'd see the dark umbral region, you would see this filamentary penumbral region, which is slightly brighter, and then that is embedded in what we call an active region, where the surface is actually brighter than the surrounding photosphere, the surrounding solar surface, because that's where the energy is coming out of. It basically, so if you have a sunspot, or if you have a magnetic field that is concentrated right here, the energy comes up. Some of that energy manages to make its way to the surface, but some of it actually comes over here and basically couples with this energy, causing this side to be brighter. And that's my lovely hand-wavy explanation of active regions. The universe is incomprehensibly big. Yeah, pretty much. Okay. Yeah, like I said, that's all I've got today. Again, if you have comments, constructive comments about this analysis, please leave them in the comment section. If you'd like to support me, then please become a channel member. I will be eventually making more channel member only videos that talk about the ins and outs of running an observatory, and specifically how the observatory is partnering with Landalt. If you'd like to support the observatory, then please consider becoming a Patreon. I use that money to effectively buy really odds and ends, power cables, containers to put eyepieces in, things that are of value but are not of huge monetary expense, that sort of thing. So, although I did, because of Judy's contributions, I was able to buy a planetary camera for our observatory. So, all right. Yeah, with that, I bid you farewell. I might actually have, I think I have an outro. Let's see.